Ever wondered how AI systems working together can be manipulated? What if I told you that even the most advanced collaborative AI, like a team of robotic soccer players, has a hidden vulnerability? Today, we're exploring a groundbreaking study that reveals how bad actors can exploit multi-agent reinforcement learning, MARL, systems with minimal effort. Let's start with the basics. MARL is the science of training multiple AI agents to collaborate, like teaching a soccer team to pass, shoot, and strategize. But here's the catch. These systems rely on aligned perceptions. If one agent sees the ball differently than the others, the entire team's coordination collapses. Now imagine a hacker infiltrating this system. Most research focuses on training time attacks, like feeding AI corrupted data during its learning phase. But this study takes a different approach: test time attacks. These occur after the AI is fully trained, like a thief picking a lock after the house is built. And here's the twist: the attacker doesn't need full access. They just need to observe what the AI sees, like peeking at a player's goggles during a game. How do they pull this off? The researchers developed two groundbreaking methods. The first, the Align attack, is like giving one teammate a blurry map while the others have clear ones. By subtly altering what one agent observes, the whole team's coordination falls apart. The second, the Hadamard attack, is even more insidious. It adds tiny, mathematically designed perturbations to the data. Think of it as static on a radio signal. These changes are so subtle they're nearly invisible, yet they disrupt the agent's shared understanding. Remarkably, this works even if the attacker can't access the AI's internal rules, only its inputs. What makes this research revolutionary? For starters, their methods are exceptionally efficient. While older attacks required millions of data points, these only need 1,000. That's like finding a needle in a haystack with a magnifying glass instead of a shovel. They tested these attacks across 22 environments, from simple games to real-world scenarios, and they worked every time. But why does this matter? As MARL systems take on critical roles, like managing traffic lights or assisting in surgeries, understanding these vulnerabilities is essential. This isn't about breaking systems, it's about building smarter defenses. By exposing these weaknesses, we can make AI more robust, ensuring it's reliable when it matters most. Imagine a scenario where a sticker on a robot's camera alters its perception of a stop sign, or a single corrupted sensor reading throws off an autonomous vehicle's navigation. These aren't hypotheticals, they're the kind of risks this research highlights. The study shows that even microscopic changes to observations can trigger a domino effect, unraveling complex strategies. So what's the solution? The researchers are asking, how do we detect these attacks? How do we build AI that's resilient to deception? The answer might lie in making systems more skeptical of their assumptions. Instead of trusting shared data blindly, future MARL systems could incorporate mechanisms to verify consistency across agents, like cross-checking observations or using cryptographic techniques to detect tampering. This isn't just about securing AI, it's about redefining how we design collaborative systems. As AI becomes more integrated into critical infrastructure, the stakes are higher than ever. The future of safe, reliable AI depends on confronting these challenges head-on. Ever wondered what happens when a team of AI agents starts doubting each other? Researchers just showed how tiny tricks can turn perfect teamwork into chaos. Let's break it down. Picture a soccer match where every player relies on the same view of the field. Now imagine an attacker placing a sticker on one player's camera, making them see the ball as a different color. That's an adversarial attack, a clever way to mess with how AI agents collaborate. But here's the twist: the attacker doesn't need full access. In one experiment, they only saw what the agents saw. In another, they saw nothing. And yet both attacks worked. How? By using microscopic changes to the agent's observations. These aren't obvious hacks, they're like whispering lies into a robot's ear. A sticker here, a pixel there, and suddenly the team's coordination crumbles. The study found that just 1,000 practice plays, or steps, could wreck the system. Even fewer steps. Still enough to cause trouble. It's like a domino effect. A tiny nudge and the whole strategy falls apart. Why are these systems so vulnerable? Because they're built on trust. MARL systems assume everyone has the same reality. Attackers exploit that trust by twisting the data, just enough to create confusion. And if this happens in a game, what about real-world systems? Think autonomous cars relying on shared data, or smart grids managing energy. A single sneaky trick could disrupt critical infrastructure. This isn't just about breaking things, it's a wake-up call. The researchers are asking, how do we spot these attacks? How do we build AI that's resilient to deception? The answer might lie in making systems more skeptical of their own assumptions. After all, in a world where AI works together, we need to ensure they're not just smart, but secure. What do you think? Could something as small as a sticker really change the game? Let me know in the comments, because the future of AI collaboration might depend on it.